Hello, let's discuss the topic a novel discrete signal processing on complex irregular graphs. Due to the explosive growth of information and communication, signals are generated at unprecedented rate. These signals possess complex irregular structures which require novel processing techniques. Graph signal processing extends classical discrete signal processing to graph signals. This has interesting applications. For example, given a graph representing the friendship connectivity in social media such as Instagram or Facebook, we sample and query their hobbies and then recover the hobbies of all users. Now, this could be helpful in targeted advertisement. To understand the real impact, we can take the Cambridge Analytica scam, where a manipulated Facebook feed could even influence US presidential elections. Another misuse of data happened in Google, where the privacy of the users were invaded for targeted advertisement. Let us review some relevant concepts of DSP on graphs. Graph shift. The graph G is represented as G is equal to V comma A, where V is the set of nodes and A is the weighted adjacency matrix or the graph shift. It represents the connections of the graph G, which can either be directed or undirected. The edge weight A and M between the nodes Vn and Vm is a quantitative expression of the underlying relation between the nth and the mth node, such as similarity, dependency, or a communication pattern. To guarantee that the shift operator is properly scaled, we normalize the graph shift A to satisfy equation number 4. Graph signal. Once the node order is fixed, the graph signal can be represented as equation 5, where the nth signal coefficient corresponds to the node Vn. Graph Fourier transform. For simplicity, assume that A has a complete eigenbasis and the spectral decomposition of A is as given in equation 6. These eigenvalues of A, that is lambda, represents the frequencies on the graph. Definition 1. The graph Fourier transform of x belongs to Cn is as equation 7 and the inverse graph Fourier transform is as equation 8. Here, the vector x hat represents the signal expansion in the eigenvector basis and describes the frequency content on the graph signal x. The inverse graph Fourier transform reconstructs the graph signal from its frequency content by combining the graph frequency components weighted by the coefficients of the signal's graph Fourier transform. Sampling and interpolation. In the previous work, the bandwidth based on the values of the graph frequencies were taken into consideration. It has three limitations. It was hard to specify the general cutoff frequency. This is because of the discrete nature of the graph frequencies. Here, the cutoff is different, but the output is same. The second limitation is that the values of the graph frequencies can't be compared between the different graphs. Here, the cutoff is same, but the values are different. And it was computationally inefficient for large graphs. Novel sampling theory. Bandwidth based on the number of non-zero signal coefficients in the graph Fourier domain is taken into consideration. Suppose we want to sample m coefficients of a graph signal x belongs to Cn to produce a sample signal xm belongs to Cm where m is less than n. In the sampling operator side, it linearly maps from Cn to Cm as in the equation 9, where m denotes the sequence of sample indices and mi belongs to 0, n minus 1. Interpolation operator linearly maps from Cm to Cn that recovers x exactly or approximately. For perfect recovery, x hat is equal to x. But in general case, rank of phi psi is less than or equal to m less than n. We consider two sampling strategies. That is, a random sampling means that the sample indices are chosen from 0, 1 to n minus 1 independently and randomly. And the experimentally designed sampling means that the sample indices can be chosen beforehand. It is clear that the random sampling is a subset of the experimentally designed sampling.
Band limited graph signals. Definition 2. A graph X is band limited when there exists a k belongs to 0 to n minus 1 such that the graph Fourier transform x hat of k is equal to 0 for every k greater than or equal to k. K is called the bandwidth of X. A graph signal that is not band limited is called a full band graph signal. Definition 3. The set of graph signals in Cn with bandwidth of at most k is a closed subspace denoted by BLK V inverse. Perfect recovery of band-limited graph signals. Theorem 1 deals with the perfect recovery of band-limited graph signals. Let psi satisfy a full rank condition. Rank of psi v of k is equal to k, where v of k is of the order n cross k and is having the first k columns of v. Then, for every x belongs to BLK V inverse, perfect recovery condition is that phi is equal to V of k into U, with U psi V of k being an identity matrix. Then, theorem 1 helps in satisfying the lower bound for sampling weight. The sampling size m should be greater than or equal to k. Proof: m less than k, rank of u psi v of k is less than or equal to rank of u less than or equal to m less than k. U psi v of k is not equal to an identity matrix. This contradicts the perfect recovery condition. Psi v of k inverse is equal to u if m is equal to k, and pseudo inverse of psi v of k is equal to u if m is greater than k. When m is greater than k, this redundancy helps in reducing noise effects. Here, if m is greater than k, we select k out of m samples for simplicity. If psi satisfies full rank assumption of theorem 1, it is called qualified sampling operator. Sample graph signal. For simplicity, consider m is equal to k. Then theorem 1 implies that for every x belongs to BLK inverse, x is equal to phi psi x is equal to phi xm is equal to v of k into u xm. This is obtained from theorem 1. And according to definition 2, it is equal to v of k x hat k. And equation number 14 implies that x hat of k is equal to u xm and xm is equal to u inverse u xm is equal to u inverse x hat k. A new graph shift is as shown in equation number 17, where lambda k belongs to C k cross k is a diagonal matrix that samples the first k eigenvalues of lambda. This leads to following theorem. Theorem 2. Let x belongs to BLK V inverse and let xm is equal to psi x belongs to CK be its sampled version where psi is a qualified sampling operator. Then the graph shift associated with the graph signal xm is given in equation number 18 with u is equal to psi v of k whole inverse. Theorem 3. For every x belongs to BLK V inverse xm minus AM xm is equal to psi of x minus AX. Proof of the same is given in equation number 90. The term x minus AX measures the difference between the original graph signal and its shifted version. This is also called the first order difference of x, while the term psi of x minus ax measures the first order difference of x at sampled indices. The connectivity information between the sampled nodes and all other nodes was lost. Despite this, AM still preserves the first order difference at sampled indices. This simulation is done to validate the theorem 3. A matrix A is considered and the eigenvalue decomposition of the same is done. And x hat is taken, and from that we compute x, and further x minus ax is also computed. And next we consider the xm as the first, second and fourth entries of x, and psi and phi are computed. Further we compute xm minus am xm, and these entries are same as the first, second and fourth entries of x minus ax. And this validates that the perfect recovery is possible. Application. For example, let's consider the specific application of sampling online blocks. Here we consider the data set of n is equal to 1, 2, 2, 4 online political blocks as neither conservative or liberal. We represent conservative as +1 and liberal as -1. The blocks are represented by a graph in which nodes represent blocks and directed graph edges correspond to hyperlink references between blocks. The graph signal here is a label assigned to the block called the labeling signal. The figure compares classification accuracies between optimal sampling and random sampling. By varying the sample size with an interval of 1 from 1 to 20, here we see that optimal sampling significantly outperforms random sampling. With this, we conclude proposed a novel sampling framework for signal graphs, and that it strongly connects classical sampling theory to linear algebra. The perfect recovery is possible when samples are band limited. And we have also talked about qualified sampling operator psi. These are the references. Thank you.